Alright guys, so I hope you're all doing well and I hope your semester is amazing. Is an amazing one. And in today's video I'll be explaining chapter 21, which is the first chapter that is covering the material that you will be tested in major 2 for the second major exam. Okay, so I'll try to upload all the videos like before the major exam, the second major exam. Unlike the first one, I missed 2 chapters. Because of some uncontrolled factors, like some things that I couldn't control in general. So, so today we'll be discussing chapter 21, and it's like your introduction to electricity and magnetism. It's the first chapter in electricity, and the rest of the course will be about electricity and magnetism. So chapter 21 is like just the shortest chapter in our course, and it's very easy. So we'll be covering about 3 topics. First, charge. We'll be discussing what charge is. Second, we'll be discussing Coulomb's law, which is a very important law in electricity. And third, we'll be discussing the idea of charge conservation. And then fourth, we'll be discussing shell theorems. Yeah, so there are about 4 important ideas that we'll discuss in this chapter. And after explaining the concepts of this chapter, I'll be solving 6 problems. 6 problems that cover the most important ideas in the chapter. And so yeah, let's get going. Alright guys, so everything in the universe, everything around us is made out of atoms. And atoms are made out of electrons and protons. So electrons represent negative charges, and protons represent positive charges. So the first thing we need to know is that we have 2 types of charges, positive and negative charges. And we have to know, or we have to really understand that when you have positive and negative charges, these 2 charges are going to attract. But if you have positive and positive charge, these 2 charges are going to repel each other. And the same thing for negative and negative charges. Okay, so how are they gonna repel and attract each other? So they're gonna exert some sort of forces on each other. So positive charges and negative charges exert some sort of forces on each other, and they can attract and repel depending on the type of charge they have. It's either positive or negative. Okay, so this here is a lithium atom. So, so as I just said, everything around us is made out of atoms. And these atoms have the same number of protons, the red ones, and the same number of electrons. So proton is the blue ones, and the red ones are electrons. So, and therefore, they are neutral. Like, the net charge on any natural atom is 0, okay? But all atoms are originally neutral or have 0 charge. But if some other atom comes and interacts with this atom, for example, it might steal one of its electrons, and therefore it will have more protons, like it will have 3 protons, and this one is gone, so we'll have only 2 electrons. So the net charge of this atom is going to be positive 1. Because we just lost an electron, and we have, so these 2 electrons are going to cancel out with these 2 protons, and we're going to be left off with 1 proton extra. So, and that proton represents positive charge. So there is something called the fundamental charge. The fundamental charge is 1.6 times 19 to the negative 19 coulombs. Coulomb here is the unit we're going to use to measure the quantity that is the charge. Okay, so this here is the charge of an electron, and it's the same charge of a proton, and it's called the fundamental charge. So any charge in the world is a multiple of this fundamental charge. Okay, K is an integer, as n being 1, 2, 3, etc. till infinity. Charge is quantized. Like you cannot have a charge of, for example, 1.6 times 19 to the 19, negative 19, plus 1 Coulomb. This is impossible. We only have multiples of E. E is the fundamental charge, and it's the charge on a proton and on an electron. Okay, so protons and electrons share the magnitude of the charge. So they have the same charge magnitude, but in order to differentiate between these two different particles, we labeled electrons to be negative and labeled protons to be positive. There is no fundamental meaning to positive and negative charges. These are just labels, like in order to differentiate between the two types of charges. So the only difference between electrons and protons, there are actually two differences. The first difference is the type of charge. One is negative, the electron is negative, and one is positive. Protons are positive. And so this is the first difference. And the second difference is that the mass of protons is higher than the mass of electrons. And other than these two differences, like the mass and the type of the charge, there is no other difference. They carry the same amount of charge, which is 1.6 times 19 to the negative 19 coulombs. Okay, so this is our introduction to charge. This is the definition of charge. And you have to memorize, or you have to understand some chemistry here, that if you have the atomic number of any atom, then the atomic number is going to be equal to the number of protons in that atom, and the number of protons in any neutral atom is going to be the same as the number of electrons in that atom. Alright, so what I need to emphasize is that all charges in nature, all charges in the universe are either E, either this number, or any multiple of this number. So as I just said, it's either E or Ke, where K is any integer. So we cannot have half of E, for example, in nature. You cannot find such a charge with this quantity in nature. So this is the idea of charge quantization. Like when you say that charge is quantized, it means that it's either E or any integer multiple of E. Like, because if you think about it, like we cannot have an electron and then 1/2 of an electron. That is impossible. So we only have like full pieces of electrons. And therefore, for example, if you have 3 electrons, then you're going to have 3E, 3 times this number, coulombs of charge. So that's aside. Like, so there is an important idea about charge. Like if you have two bodies, like if you have a ball, for example, and we have let's call this ball A, and we have another ball B, and ball A has the exact same size as ball B. So this is very important. The size has to be the same for this to work out. And we have some sort of charge on here. Like we have 1, 2, 3, a positive 3 charge on the A. And we have a negative 5, okay? Negative 5 coulombs on B. And these two balls have the same size, okay? And then we bring these two balls next to each other and make them touch, so to speak. Then what's going to happen to the charge on these two balls? So the first thing that is going to happen is that we're going to add the charges. We're going to get, we're going to have to get the net charge on both balls. So positive 3 on A, negative 5 on B is going to be equal to negative 2. So this is the first step. This is the first thing that's going to happen. The charge in both balls are going to add, okay? Okay, so they're just touching, like, they don't go into each other, like, as I just drew. But anyways, so after being added, after the charge is added, what's going to happen is that we're going to separate these two balls back the same distance away from each other. And now think about what's going to happen to the quantity or the charge on these two balls. Like what charge are we going to have in B and what charge are we going to have in A? Okay, so in electricity we have a perfect justice system. Like keep that in mind. If the size of the balls are the same, then if you make them touch and then separate them, and then you add the charge, then you're going to have the same exact charge on both balls. A perfect justice system. Okay, so we're gonna have a -1 charge here and a -1 charge here. So this is basically dividing the net charge equally to both balls. Like, so this idea is very important to understand, and you're gonna use it to solve problems in this chapter. So this process of equal justice system of dividing charges to be equally to the same on both balls only works if we have two bodies of the same size. Like if the size is different, then there is another sort of justice system. Like, for example, like we don't have to understand this at this point, but just to clear things out, like if you have ball A bigger than ball B, then if you make them touch and then separate them, then ball A are going to have more charge. Like when you divide the net charge, more is going to go to A. So that's why I said it's a perfect justice system. So it's proportional to the size. But in this chapter, we're interested in balls of the same size. So we're not going into here yet. Like we will go there later. But this is the idea of charge conservation. The idea of perfect justice system and charge conservation. Okay, so charge conservation says that the net charge means the sum of the charges, of all charges in our closed system, is always going to be the same. It does not change. So what happens is that we get equal distribution of charge between the two exactly the same size objects. And that's it. That's all you need to know about this important aspects for chapter. And on to the next one. Alright, so now you understand some things about charge and how same charges repel and how different charges attract. So I want to go over, briefly go over some concept that is called induction, okay? Imagine we have some sort of conductor here. So the conductor has positive and negative charges, okay? And any conductor, by definition, is a material that has some free electrons. Okay? Free electrons means that the nucleus of the atom does not pull on the electron very strongly. Like the force that is the nucleus is pulling on the electron is not as strong as the other ones, the other electrons that are moving closer to the atom, or closer to the nucleus of the atom. Okay, so because this electron is far away from the nucleus, the force of attraction between the electron and the nucleus is not strong. Like it's actually very weak. Because it's weak, this electron is called free electron. A free electron. So inside this conductor, let's say it's iron, for example. Any metal is a conductor, okay? A conductor is a material that has some sort of free electrons that can move out from one atom to another atom. So it can move through the surface. Okay, so this is a conductor, a conductor. And we said, for example, it's an iron piece. Okay, and if we bring here a rod, let's say a positively charged rod, and we don't touch this iron or piece of iron, then what's going to happen is that the free electrons are going to be attracted, and we're going to have something like this. So we're going to have all the electrons here concentrated near the rod, and all the protons away from the rod. So this idea right here is called induced charge. Like we induced a negative charge in here, and this can only happen if we have some sort of free electrons, and free electrons is like something that changed the world. Like a lot of technology is based on this idea of free electrons. So free electrons get attracted to our positive charge, and this process is called induction. Okay, so next we're going to have our most important lesson in our chapter, which is Coulomb's law. Alright guys, so here is the most important idea that we need to learn or take out from that chapter 21. And it is Coulomb's law. So what does Coulomb's law say? Like, it says that if we have two charges, like if you have a negative and a positive charge, for example, then there will be some sort of electrostatic force exerted on both of the charges. And that force is going to be attractive if the two charges are different. In fact, this charge are going to exert a force on this charge, an attractive force, which means the force is going to be heading in that direction, in the direction of the positive charge. And the magnitude of this force is going to be equal to the quantity, or the magnitude of the first charge, let's call this Q1, and times the magnitude of the second charge, divided by the distance between them squared, okay? So, the quantity, the force, is inversely proportional to the distance, which means the larger the distance is, like the more far or the further away the charges are from each other, the weaker the force is going to be. Okay, so magnitude of the first charge times the magnitude of the second charge divided by the distance between them squared, multiplied, the whole thing is multiplied by k. So k is a constant, and it's equal to 1 over 4 pi, this is another constant, and it's equal to this quantity, okay? So we're not really much interested in how we derive these constants, but we're very interested in Coulomb's law. So we said that the positive charge will exert a force on the negative charge that is heading towards the positive charge, because this charge is different than this charge. If this charge was positive, then we're going to have the same force, but in the opposite direction. So we're going to have this force only if Q2 is positive. Okay, but we're not done yet. There's something else going on here, okay? So this charge is going to do the same thing to this charge. It's going to exert a force on it, an attractive force. Attractive because it's different. It's positive, and this one is, this negative, and this one is positive. And the magnitude of this force is going to be equal to this. So these two forces, so I'm going to erase this here because I don't want to confuse you guys. Okay, so these two forces are equal in magnitude and opposite in direction. And the way we calculate the force is just by multiplying the constant times the two charges over the distance squared. And in fact, this law, Coulomb's law, is very similar to the Newton's law of gravitation that we studied in 101 in the last course, or the previous course. So this here, the law of gravitation, has the same exact idea. Like, it says that if you have two masses, then we're going to have some sort of force acting on the first mass due to the second mass. And we're going to have the same exact force, but in opposite direction, acting on the second mass due to the first mass. Okay, so these forces are vectors, okay, vector quantities. And in order to solve problems for using Coulomb's law, you need to understand, like deeply understand how to add vectors and how to work with vectors and whatnot. Okay, so one very important note that I want to add is that if you have a positive and another positive charge, for example, then the force acting on this charge is going to be repulsive, because these two are the same, this force is going to have the same sort of alignment as the other charge. Like we're not going to have an angle, like a force that is acting on this with an angle like that, because this charge is aligned with this one. But if we have another charge like here, then the force is going to be coming straight out of this charge onto this charge. So you have to, when you work with vectors, like you have to understand these sorts of alignments, and you know, you need to know how to work with angles and whatnot. Okay, so our last topic that we're going to discuss. All right, guys. So our last topic that we're going to discuss in this video will be our last conceptual topic will be shell theorem. So if we have some sort of shell, and a shell is like a hollow sphere or something like that. So and on the inside we have some sort of vacuum, and okay, so and the frame of this shape or of this shell is positively charged. Okay, so we have some charge Q2 on this shell. So and we have a point charge right here. Like say we have a negative charge, a negative point charge right here, and we have a positive Q2 or a shell charge. Then how are we? How do we calculate the force, the electrostatic force done between these two charges? Then shell theorem simply says that we can assume, or we can solve the problem as though the charge is concentrated in the center of the shell. Like if we have like 5 or 3 coulombs here distributed around the shell, then we could assume that this 3 coulombs is basically in the center of the shell, and then calculate the distance between the center and our point charge, and then use this Coulomb's equation to calculate the electrostatic forces acting on both the frame and the point charge. So this shell theorem is very similar to the one that we studied in our last course, but the only difference is that here we're dealing with electrostatic forces, and there we will dealing with gravitational forces. So one thing that we need to note is that if we move this point charge, if we take this to the inside of the shell, and we know that the whole shell is charged with 3 coulombs, then according to the theorem, the shell theorem, that it says that the electrostatic forces on this Q1 is going to be 0, okay? 0. And that is true for any point inside the shell. Like even though that shell is positively charged, if we take any point charge into the interior of the shell, then the electrostatic forces, the sum of the electrostatic forces acting on it, will be 0. And that's it. This is a pretty straightforward and fast chapter. And now we'll be solving 6 problems. And because this chapter is short, I'll be integrating the concept with problem solving. All right. All right, guys. So our first question right here is a question that is asking. It says that if we have 1 kilogram of helium, so we know the atomic number of helium. The atomic number is given in the question, and it's 2. What does it mean to have an atomic number of 2? It means that the number of protons is 2. And if the atom is neutral, the number of electrons must as well be 2. And we're talking about neutral atoms here. He said helium, he didn't say ion or anything like that. Alright, so we want to figure out the charge on 1 kilogram of helium. Okay, so we know the molar mass of helium. The molar mass is basically 4 grams per mole, which means that if we have 4 grams of helium, then we have basically 6.022 times 10 to the 23 atoms of helium. So this is the meaning of molar mass. molar mass is measured in gram per mole. Like the SI unit is kilogram per mole, but this is the SI unit, but for historical reasons, that molar mass has only been written in grams per mole. And it is the unit that is used in this question. We have like the molar mass to be 4 grams per mole. Okay, so we want to figure out, in order to figure out the charge of this 1 kilogram of helium, first we want to figure out how many atoms in 1 kilogram, number of atoms. Okay, how can we figure that out? Like, we know that the molar mass is 4 grams per mole. So if we have 4 grams of helium, we have 1 mole of atoms. 1 mole is equal to Avogadro's number. Avogadro's number is basically 6 times 10 to the 23. But we're not interested in 4 grams because we have 1 kilogram. So we want to somehow convert this 4 grams into 1 kilogram. So first, we divide both sides by 4. So 1 gram of helium is equal to 1/4 of Avogadro's number, or 1/4 of the mole. Okay, so we're almost there. One step, like to get to our 1 kilogram quantity that we're looking for. All right. So if you multiply, if 1 gram is equal to 1/4 of a mole, then 1 kilogram is like 1,000 times higher or more than this quantity. So just multiply both sides by 1,000, and you'll be getting that 1 kilogram of helium is equal to 10 to the power 3 over 4 moles, which is basically 10 to the power 3 over 4 times Avogadro's number. So this quantity right here is basically the number of atoms. So if you have 1 kilogram of helium, then we're going to have this number of atoms. Okay, number of atoms. So then we know that 1 atom of helium has 2 electrons. So we multiply this by the number of electrons. And now we have the number of electrons in 1 kilogram of helium. So all that is left to figure out the charge on this kilogram, 1 kilogram of helium, is to multiply our number, the number of electrons, by the charge of the electron. So the electron charge is a fixed number, and it's 1.6 times 10 to the negative 19 coulombs. And if you multiply these 3 numbers, like E, together, you'll be getting the charge in the electron charge in 1 kilogram of helium. And that will be your answer, 4.8 times 10 to the 7. Alright guys, so question number 2 is one of the most challenging questions I've ever seen from Professor Kunwar, and let's get going. It says in the question that we have 2 identical balls. So ball A and ball B have the same exact size. And we have some sort of separation between the balls. Let's call the separation R. So R is given the problem, and it's 8.4 centimeters. Alright, so we have some sort of attraction or attractive force acting between the 2 balls. And from that, we can infer that one of the balls is positive and one of the balls is negative. How did we know that? Because we already know from our conceptuals that when you have 2 different charges, the forces between them, the electrostatic forces, are going to be attractive. It says in the question that we bring the balls together and let them touch each other, and then separate them the same distance, 8.4. R is the same as this R. And after we do this, our perfect justice system that we just talked about kind of works out here. It distributes the charge. First, it adds Q1 plus Q2. It adds this and this, and then divided by 2. And then we eventually get this charge on here, on this ball, and this same charge on this ball. And because the charges are now equal in this ball and this ball, the forces become repelling each other. The balls, they start repelling each other because they have the same charge. The only difference that we have at this point is that the repulsion force is 10 times weaker than the original attractive force. So our equation becomes 10 times F prime is the new force, the repulsive force. Alright, so our equation becomes something like this. So we know that the electrostatic force is, according to Coulomb's law, is equal to K times charge 1 times charge 2 over R squared. And we know here, on the left side of the equation, that describes this here, the situation after the ball touched and then separated. We know that Q is the same on both balls. So this Q prime times K multiplied by 10, because we know that it's 10 times weaker according to the question. Okay, now the question is asking about this value right here. We don't know what kind of charge on the ball, on any of the balls we have after the perfect justice system process happened. So when I say perfect justice system process, I just mean that we took the ball and let them touch each other and then separated them again. Alright, so in order to figure this quantity out, we need to solve this equation. But we have 3 unknowns in this equation. We have Q prime, we have Q1 and Q2. So we're going to try to rewrite Q1 and Q2 in terms of Q prime. Okay, so we know Q prime is equal to Q1, the charge on Q1, and we assume that it's negative, okay? Which means the exchange, the charge exchange, will be subtracted from this value. So we know that the charge exchange, this is also a given in the problem. The charge exchange in this process, the perfect justice process, is 70 microcoulombs. So since this is positive, since this is negative, then it's going to lose some sort of charge to this ball when we let them touch each other. Alright, so our Q prime is going to be equal to Q1 plus Q, which is, I labeled Q as the 70 microcoulombs, which is the charge exchange. And our Q2, since it's the positive ball, it's going to gain electrons. So we can write that Q prime is going to be equal to Q2 minus Q, or 70 microcoulombs. Okay, then just rearrange your equations and write them in terms of Q1 and Q2. And now we have expressions for Q1 and Q2 in terms of Q prime. Alright, so take this equation here and kind of zoom into it. And you will see that the left side of the equation, which we have already explained, that we have Q prime times K over R squared times 10 is going to be equal to the left side, so the right side. So the right side on here is just the same thing as here, but we rewrote Q1 and Q2 in terms of Q prime. Okay, so we know K is the same on both sides, so we cancel K out. We know that the separation between the balls before the perfect justice process happened and after the process happened is the same. R is always 8.4, so we can cross that out as well. So we're left out with this expression right here. Okay, how did we kind of rewrite this to become like this. So remember your math formulas. Like if you have a difference between two squares, we can just rewrite that difference as this quantity right here. So we rewrote this quantity as this quantity, and then we took this here to the other side. So we have 9q prime squared is equal to negative q squared. Okay, so we know q, we have defined q as being 70 microcoulombs, so it's 70 squared. Now just plug this here to your calculator and you'll be getting this answer, 32.3 with a marginal error of 5%. So and that will be the value of q prime, or the charge on any spheres, or any sphere after the charge exchange happened. Alright guys, so for question number 3, so we're given that at the origin, so we have the x-axis and we have the origin. So we're given that there is a charge q1 at the origin with a value of 50 microcoulombs, and there is another charge 6 centimeters away from the origin, let's call it q2, and there is a third charge. This third charge is 15 meters away from the origin. So here is centimeter, here is meters. Okay. And we want the sum of the electrostatic forces on Q3 to be 0, okay? Okay, so if we know that the sum of forces on 3 is 0, and we know this charge is 50 microcoulombs, and it's positive, and here it's negative. So we know that the force due to this charge, because it's positive and this one is negative, is going to be attractive to the charge. So let's call it F1, okay? So F1 is the force of Q1 on Q3. So in order to kind of counterbalance this force and make the sum of the forces on Q3 to be equal to 0, we need to have a force in the opposite direction. Which means that Q2 is going to be a negative charge. Okay? Why? Because negative and positive, negative and negative are going to repel, and the resultant force is going to be in this direction, and that's exactly the direction we want it to be in order to make the sum of the forces is equal to 0. Okay, so not only is the sign must be negative, but the magnitude of the force from Q2 to on Q3 must be equal to the magnitude of the force exerted by Q1 on Q3. So this here is Coulomb's law. K times the charge one, the first charge times the second charge over the separation between them squared. Okay, as you can see here, the Q1 and Q3 are both known, and the separation is known as well. So we just plug our values in. Right here, we don't know what Q2 is, but we want to solve for it. So we want this here to be in such a way that makes the force, or F2, equal to F1, as we set it up here in our equation. So we don't know what the value of Q2 is, but we know what Q3 is, which is given in the problem, over the separation between them squared. Okay, so what is the distance between this here, Q3 and Q2? So I made a little bit of a mistake over here. Okay, so the distance here, the dotted line distance, is equal to 15 minus 15 meters minus this distance. So this distance is basically 6 times 10 to the negative 2 meters. So if you plug this number into your calculator and click shift solve, you'll be solving for Q2 and you'll be getting this value. So this is the value of Q2 that will make the sum of the forces on Q3 to be equal to 0. And that will be your answer. Alright guys, so question number 5 is our easiest question on here. And it says we have two balls. We have ball A and ball B. Ball A is charged with negative 13 nanocoulombs and B with positive 5 nanocoulombs. So what we did is that we brought these two balls next to each other and let them touch each other and then separated them. And he's asking what is the new charge in here? So this is pretty straightforward. We calculate that through our perfect justice system. Since the two balls have the same size, we first take or calculate the net charge after we sum or after we let them touch each other. So the net charge right here is going to be 5 minus 13, which is going to be negative 8. So this here is negative 8. And then after we calculate the net charge, we separate this charge equally between them. Very equal, because these two balls have the same size. So we divide this by 2. And that is going to be equal to negative 4. And that is the answer for part A. He's asking for the charge on A after the separation. Alright, so part B is asking how many electrons were transferred in this process. So in order to move from negative 13 to negative 4 nanocoulombs, it means that we have transferred 9 nanocoulombs. Because the difference between the magnitudes of 13 and 4 is 9. So how many electrons are in this number? 9 nanocoulombs. Okay, so first things first, let's convert this into coulombs. So 9 times 10 to the negative 9, which is equal to our charge transferred in coulombs unit. Then divide that by the charge of 1 electron, which is, we know it's a given value in coulombs. So if you divide this value by this value, you'll be getting the number of electrons. And that would be something like this. So it's going to be 5.6 times 10 to the 10. And that is your answer. Alright guys, so in our last question here, question number 6, it says we have an equilateral triangle, which means we have a triangle with all the sides are the same. So all the sides have the same length. As a result, all the angles are going to have the same measurement as well. It will be 60 degrees. And we have charges on the vertex, on each vertex of the triangle. So we have this charge, 2 positive charges on here, and 1 negative charge up there. And we're asked to calculate the net force, or F net, on C, the electrostatic force on C. Okay, so since the triangle is a 60 degrees triangle, then we know that B will be pulling on C with a force in this direction, and the force is like 60 degrees away from the horizontal. Because we know that these two angles must be the same, because these two lines are horizontal, and this is a line that's crossing two horizontal lines. So this is something that we took in kind of middle school. So in general, the first step to calculate this is to calculate the force of B on C. The force of B on C is just calculated using Coulomb's law. K times the charge of the first one times the charge of the second one over the separation times our conversion factor. And by the same way, you calculate F of A on C. So after you do that, you'll be calculating the whole vector force of B on C. So we're asked to find the net force. So we need to add these two vectors, f of A and f of B. So in order to do so, we know to kind of decompose each vector in its x and y components. So we know that f of B is basically two vectors. One that is like this, and the other is like this. Okay, and the sum of these two vectors is equal to f of B. Okay, so in order to figure out the x component of B, we multiply the whole vector f of B by cosine 60, and you'll be getting this component. Okay, keep in mind that f of A is in the opposite direction of f of B. So its x component will be in this direction. So minus f of A times cosine 60, and that is going to be net f net x. And by the same logic, you get f net y, and that is net, this is net. The net force is acting on x, and here is the net force is acting on y. And then by Pythagorean theorem, you just get the magnitude of the whole net force acting both in the x and y directions, and that is going to be 4.4 newtons. And that would be your answer. So this question is basically a question that is testing you on vectors or vector analysis. The only thing you need to know, like for this chapter, is basically Coulomb's law. Everything else is basically vector analysis. So make sure you get this straight. Your vector analysis techniques. You know, this is something we learned in 101. So make sure you review them or something like that. Okay, and that's it for today. That was chapter 21, Coulomb's law, and it was like an introduction to electricity and magnetism. And after we explained the concepts, we solved 6 problems. So feel free to comment down below, let me know your suggestions and whatnot. And I'll see you guys in another video.